Welcome to part 1 of our lesson on section 3.2, the derivative as a function. In this lesson, you'll learn about the differentiability of a function and about the relationship between differentiability and continuity. By definition, a function f is differentiable at some number a if its derivative at a exists. In our first example, let's consider the function f of x equals absolute value of x. In part A, we're asked to use the graph of the function to explain why it doesn't fit the definition of differentiable at 0. The derivative at 0 will only exist if the limit of the slope of the secant lines around 0 exists. In turn, this means that the limit of the slopes of the secant lines on the left side of x equals 0 must be the same as the limit of the slopes of the secant lines on the right side of x equals 0. So maybe we should answer part B first. Part B asks us for the limit of the slopes of f as we approach x equals 0 from the right and from the left. The slopes are all 1 on the right, so the right-hand limit is 1. The slopes are all negative 1 on the left, so the left-hand limit is negative 1. And this brings us to why f is not differentiable at 0. The slopes approaching from the left-hand side are not equal to the slopes approaching from the right-hand side, therefore that limit can't exist at 0. You can imagine that the derivative cannot exist at a point where any graph has a sharp corner on it, because we'll end up reaching the same conclusion as in example 1. Since the slopes on both sides of any corner will approach different values from both sides, the limit of the slopes can't exist at that point. Thus, we can conclude that wherever a graph is not smooth, it won't be differentiable there. A sharp point on a graph is sometimes called a corner or a cusp. In the second example, consider the function f of x equals absolute value of x squared minus 4. This will have the same graph as the parabola y equals x squared minus 4, except that the points on the parabola that have negative y coordinates will become points with positive y coordinates instead. To graph f prime for part A, follow the graph of f from left to right. The slopes are negative, increasing to become slightly less negative, but then the derivative doesn't exist at x equals negative 2 because the graph has a cusp there. Continuing to the arch between negative 2 and 2, the slopes are large and positive at first, decreasing toward a slope of 0 at x equals 0, and then continuing to decrease into negative slopes. Then in the last section of the graph, the slopes are positive. Based on the symmetry, they're probably the opposite of the slopes in the first section. At this point, you're not expected to be able to estimate the exact value of the non-zero slopes, but you may have figured out from previous problems that the derivative of a quadratic is linear. For part B, to graph the derivative of the red graph, the slope of my leftmost piece is approximately 2. The slope of the middle piece is about negative 2. And then the slope of the last piece is 2 again. Part C asks if a graph is continuous at A, does it guarantee that it is differentiable at A? Our answer here must be no. In this graph, we can see that f is continuous at negative 2 and 2, but it is not differentiable at either of these numbers. Also, in example 1, f of x equals absolute value of x was continuous at 0, but not differentiable at 0. And then for part D, based on what we've seen so far, we might be able to say yes to that, but it's a lot harder to prove that something is true than to prove that it's false. So it turns out that part D is true, and here's the proof. We're going to show that if f is differentiable at A, then it must also be continuous at A. In symbols, this means that we need to show that using the limit definition of the derivative, if this limit exists, then the limit of f of x as x approaches A has the same value as f of A. You might remember that last part as the definition of continuity. Let's work with the limit of f of x as x approaches A first. Using the laws of algebra, I can subtract f of A and add f of A and expect the value of this limit to be the same as the original. By the limit laws, I can separate this into the sum of two limits. Now I'm going to work with that first limit separately. Again, using algebra, I can multiply the numerator and denominator of this expression by the same value, in this case by x minus a, and use the limit laws to separate this into the product of two limits. Substituting a for x in the first limit results in 0. The second limit is the derivative of f at a, which we know exists because that was our given information. These multiply to equal 0, making the limit of f of x minus f of a as x approaches a equal to 0. Now keep in mind that if the derivative at a did not exist, we might not be able to conclude that this limit was 0. Now let's go back up to the first part of our work. We can substitute 0 in place of that first limit, and the second limit is f of a regardless of what x equals. We've just proven that if the derivative at a exists, then the limit of f of x as x approaches a is f of a. In other words, putting that all together, we can conclude that a graph is not differentiable at a corner or cusp because the slopes approach different values from both sides at that point. A graph is not differentiable at a discontinuity. The slope can't exist if there's no point there. And lastly, the graph will not be differentiable if it has a vertical tangent at that point. This last graph would have a vertical tangent line at the point -2, 1. Since the slope of a vertical line is undefined, the derivative at this point does not exist. In our last problem, the graph of f is shown below. It has a vertical tangent at 2 and horizontal tangents at 1 and 3. In the interval between -2 and 4, when is f not differentiable? Pause the video now if you'd like to think about the answer before I give it away. We now know that the graph is not differentiable where it has cusps, discontinuities, and vertical tangents. There are no cusps in this graph, but I can see a discontinuity at 0. We can eliminate choice C because it doesn't list 0 in it. There's a vertical tangent at 2, so 0 and 2 are the only places where f is not differentiable. That means our answer is B. This concludes our lesson on Part 1 of Section 3.2, the derivative as a function.